Chapter 7, Concurrent and Parallel Forces. This lecture will help you understand how to use the center of gravity to solve parallel force problems. In our introduction to parallel force problems, we ignore the mass of the plank the painter was standing on. The plank cannot be represented by a single point. We say it is an extended object. The center of gravity of an object is that point at which all of the weight can be considered to be concentrated. In solving parallel force problems, we represent the weight of a body as a vector through its center of gravity. A carpenter stands 2 feet from one end of a 6-foot scaffold that is uniform and weighs 20 pounds. If the carpenter weighs 165 pounds, how much weight must each end support? Assume rotation about point A. We begin with the equilibrium condition on forces. The two support forces F1 and F2 point up and are positive. The weight of the man and the weight of the scaffolding point down and are negative. We use the known weight of the man and the plank to find the sum of the two support forces, which is 185 pounds. We again write the equilibrium condition on the torques. F1 is at the pivot point and gives no torque. The man is 2 feet from the pivot point and provides a clockwise or negative torque. The plank itself provides a negative torque in the clockwise direction. The distance must be 3 feet. That is the center of gravity. The center of gravity can be found by supporting the plank or any object by one support. The point where the plank does not fall is the center of gravity. Try this with a meter stick or yardstick. They will balance at the center, 18 inches for the yardstick and 50 centimeters for the meter stick. The final force is the right support force, F2, and it provides a counterclockwise or positive torque. Since the left support force provides no torque, we can find the right support force, F2, as 65 pounds. Since we have a relation between the left and right support forces from the equilibrium condition of the forces, we can find the left support force at 120 pounds. Find the magnitude, direction, and placement from point A of a parallel vector F6 that will produce equilibrium in the parallel force diagram below. Notice in this problem that the position and the direction of F6 are not indicated. We must find both. We again start with the equilibrium condition on the forces. When we write the sum, we include the unknown force F6. All the forces are known, and we find that F6 must equal 2,630 newtons. Pointing up. We now use the equilibrium condition on torques using point A as the point of rotation. Keep in mind that the final answer must be from A, not A prime. We write the sum of the torques as the sum of the forces times their distances from the pivot point, A prime. I use primes on the x's to indicate that the distances are measured from A prime. Now I fill in what I know. Looking at the diagram, F1 provides no torque about A prime. F2 provides a clockwise torque about A prime and is negative. F3 provides a negative torque. F4 provides a negative torque. F5 provides a positive torque and points up. F6 we know points up, but we don't really know if it is to the right or to the left of A prime. If it is to the right, it provides a positive counterclockwise torque. If it is to the left, it provides a negative or clockwise torque. I guess at positive. If F6 is to the right of A prime, the distance will come out positive. If F6 is to the left, the distance will come out negative. Finding x prime gives us a distance of positive 3.23 meters. I guessed correctly. This is the distance from A prime, but I want the distance from A. I notice that A is 1 meter to the left of A prime, so I need to add 1 meter to the distance from A prime to get the distance from A, which gives 4.23 meters. F6, therefore, is a 2,630 Newton force, 4.23 meters from the left end and pointing up. This assures the plank does not fall or rotate. According to Newton's first law, if an object is at rest, it can be said to be in a state of static equilibrium. In other words, all the forces cancel out so that the net force is equal to 0. Since torque is the rotational analog to force, we can say that if a system is at rest, all the torques cancel out. The figure shows two objects, an elephant and a mouse. It is possible to place both on a sufficiently strong seesaw and have it balance. If you have ever gotten on a seesaw with a heavier person, you know that to make a balance, the heavier person must be closer to the pivot point, and the lighter person must be farther away. Thus, the elephant and the mouse can balance if the elephant is really close to the pivot point and the mouse is really far away. Suppose a 4,600 kilogram elephant were placed on a seesaw with a 0.025 kilogram mouse. The elephant is placed 10 meters from the point of rotation, the fulcrum. How far from the point of rotation would the mouse need to be placed so that the system exists in a state of static equilibrium? The counterclockwise torque from the elephant must balance the clockwise torque from the mouse. Since the force is the weight, we can substitute the mass times the acceleration of gravity for the weight. Including what we know everything except the mouse's distance. Solving for the mouse's distance, we get 1.84 times 10 to the 6 meters, which is around 1,433 miles. While possible, this is not a very practical answer. Find the net torque on the wheel in the figure about the axle through O, taking A as 8 centimeters and B as 25 centimeters. The 10 Newton and 9 Newton forces give a clockwise torque. The 12 Newton force gives a counterclockwise torque. We are going to find the net torque acting on the wheel using our definition of torque as force times distance from pivot point times the sine of the angle between them. The 10 Newton and the 9 Newton forces are both at 90 degrees. But what about the 12 Newton force? You might be tempted to use the 30 degrees in the figure, but the 12 Newton force is perpendicular to the radius A, unless the angle between them is 90 degrees. They are all perpendicular forces. The sum of all the counterclockwise torques is 0.96 Newton meters, positive since they are counterclockwise. The sum of all the clockwise torques is minus 4.78 Newton meters, negative since they are all clockwise. The net torque is the sum of the counterclockwise and clockwise torques. In this problem, the sum is minus 3.79 Newton meter. This means we do not have an equilibrium condition. The wheel will change in rotation. The direction of the change is negative, clockwise. A hungry 700 Newton bear walks out on a beam in an attempt to retrieve some goodies hanging at the end. The beam weighs 200 newtons and is 6 meters long. The goodies weigh 80 newtons. When the bear is 1 meter from the end, find the tension in the wire. We take the point of rotation to be the hinge. The weight of the bear and the weight of the beam point down. The weight of the beam itself is drawn at its center of mass. The weight of the goodies is at the end of the beam and points down. The tension in the wire points up and to the left. The free body diagram looks like this. All the forces are drawn in their correct direction and location. The torque due to the bear is minus 700 Newton meter. The torque due to the beam is minus 600 Newton meter. The torque due to the goodies is minus 480 Newton meter. The torque due to the tension is 5.19 meters times the unknown tension. Since the system is in equilibrium, the sum of the counterclockwise and clockwise torques must be zero. Summing all our torques and solving for the tension, T, gives 340 newtons. Two stubborn men are trying to use a revolving door. The door has a diameter of 2.6 meters. The man on the left exerts a force of 625 newtons perpendicular to the door and 1.2 meters from the center, while the one on the right exerts a force of 850 newtons perpendicular to the door and 0.8 meters from the center. Find the net torque on the revolving door. Which man wins the battle? The torque on the left is due to the man on the left and is equal to 750 Newton meter. The man on the right produces a torque of 680 Newton meter. Since the torque on the left is greater than the torque on the right, the man on the left wins and the revolving door rotates clockwise. Summarizing the center of gravity, for objects equal in mass, the center of mass is equally distant between the two. For unequal masses, the center of gravity is closer to the more massive object. Massive objects, such as planets and the sun, actually orbit about their common center of mass. If one object is much more massive than the other, the center of mass is not far from the center of the more massive object. The following are a set of problems for you to work on. Pause the video to give yourself time to work on the problems. 8 people are involved in a tug of war. The blue team members pull with forces of 220 newtons, 340 newtons, 180 newtons, and 560 newtons. 3 members of the red team pull with forces of 250 newtons, 160 newtons, and 420 newtons. With what force must the fourth person pull to maintain equilibrium? Pause the video to work on the problem. Did you get 470 newtons? Find the tension in each cable shown in the figure. Pause the video to work on the problem. Did you get the T1 is 348 pounds and T2 is 426 pounds and that T3 is 475 pounds? Louisa, whose mass is 45 kilograms, is standing at the end of a 5.5 meter diving board, which has a mass of 35.7 kilograms. What force must the bracket and fulcrum exert on the diving board? Where would Louisa stand to have both the fulcrum and the bracket apply an upward force? Pause the video to work on the problem. Did you get that the force is minus 2,550 newtons and that Louisa would have to stand between the bracket and the fulcrum to apply an upward force? Your assignments are to read Chapter 7 in the textbook and watch the videos on Blackboard. Your homework assignments are due March 2nd.